So hi everyone, this is the third video in this Galois theory recap for our AG codes course. In this particular video, we are going to talk about Galois extensions. Okay, so let's look at definition 15. We'll get back to 14 in a second. So when you have a finite extension m over k, and recall that finite is in particular algebraic and also finitely generated. We'll use that later on. So when you have a finite extension, we call it Galois if it is both normal and separable. That's the vanilla definition of a Galois extension. You need both the kind of orthogonal properties that we already talked about. So that's a nice definition to work with, but actually it's not completely insightful, and it's and we'll see actually most of this lecture will be about giving a characterization of Galois besides as the like intersection of these two properties. Okay, so let's go back to definition 14. So again, let's let m over k be a finite extension. We are going to associate with this extension a group that's called the Galois group, and it is denoted like that, gal m over k. And what are the objects here? So these are all automorphism, field automorphism of M that fix all elements of K. So again, so this Galois group, or first of all, as a set, these are all automorphism from M to M that acts as the identity on K. They fix each and every element in K. And it's clearly a group. I mean, this is a group, and this is a property that is closed under compositions, and the identity is clearly an element here, and you have closeness to inverses and so forth. So that's a group. And so we are going to kind of understand and study this group. The general thing about Galois is that the field extensions correspond to groups in a sense, right? You can understand field extension by understanding the corresponding groups. Okay, so in definition 16, we are doing the following. So again, we're looking at this finite extension M over K with its Galois group, which we always denote just by G. And we denote by Mg the set of elements of M that are fixed by all automorphisms in G. Right, so Mg is, we know that all automorphism in G fix every element in K, but potentially they can fix a larger set in K, and we denote that set by Mg. So Mg is a superset of K, and it's easy to see that it's also a field. So it's a field extension of K, and clearly by definition, it's a subfield of M. Okay, so this Mg is kind of the real thing that is being fixed by all elements in the Galois group of M over K, which potentially may be larger than K. So a lemma that we will use throughout is the following. So it gives you kind of a bound on how large the Galois group of an extension can be. So say you are looking at a finite extension again, then the Galois group is always bounded in size by the index of the extension M over K, which is finite because we assume the extension is finite. Okay, so this little paragraph here just reminds you of something that we talked about. So say you have two fields K and L, and there is a field homomorphism between them. Right, and you can think of this for a second as a ring homomorphism between them. Forget about the fact that you have inverses and so forth. Then you know that what I want to say is that if these two are fields, actually, if K is a field that suffices, then phi must be an embedding. Namely, phi is one-to-one. And I think of it as an embedding because phi is one, you can identify K with its image phi of K because there are no collisions within L. So in that sense, we embed K into L by looking at phi of K, which is the same as K essentially. And the reason that this is an embedding, we talked about it once, is that right, as a ring homomorphism, we know that the kernel of the map is going to be an ideal in this ring, which is a field. And the only ideals that you have in a field are the two trivial ideals, 0 and K. Now, we always assume that phi of 1 is 1. Like we always take ring homomorphisms with units. We always kind of, in some communities you don't do it, but we do it. We specify that initially. The ring homomorphism sends the units to the units. And so this means that the kernel cannot be everything because there's something that doesn't go to 0. So the only options left is that the kernel is 0, which means that, that this is a bijective, an injective map. Okay, so that's that. So when I say field embedding, I really mean any ring homomorphism from this field to that ring or field. Okay, so the lemma tells us the following, and here's the picture. You have a field K, and you have a map from K to L. That's phi. That's this one here. It's a field embedding. That's what we talked about just now. And let's say you also have a field extension of K. So M is a field extension of K, finite field extension of K. Then you can ask, how many ways are there, or how many embeddings are there of M to L that extends phi, right? So how many ways, how many embeddings for M to L you have? In other words, for which this diagram commutes. So doing this or doing that is the same. But really the way you should think about it is in how many ways you can extend phi from K to M, getting at the end, not just a map, but an embedding, of course. Okay. And the answer is that the bound is at most the index of K and M, independent of L. Okay. So let's see why this is true. And again, I'm only doing that so that you'll be refreshed about these kind of techniques from Galois, because we are not just going to use the theorems, we are going to need to prove some things that you usually don't see in Galois theory courses, and that's why you need to kind of remember not only the results and the bottom lines, but also the proof techniques. So, okay, so let's see how you bound this. So first of all, as M over K is finite, that's the assumption here. You know that it's finitely generated, right? That's an easier, simpler thing. And we said, right, that if you are finitely generated and algebraic, then that's equivalent to finite and so forth. We won't be needing it here. So there are some finite number of generators that together with K generates all of M. And by the way, I should say, we'll talk about it later, that in characteristic 0, it suffices to have one generator. I mean, you're guaranteed to have one generator in every finite separable extension, but that will be later on. So for now, we have this finite number of generators, and we are going to work one by one. So the picture from before, instead of M, I'm going to write K of alpha 1, and then extend it and so forth. So let's look at this triangle initially. So how many ways do you have to extend this map phi from K to K of alpha 1? When, what you really have to do is to, any such extension must map alpha 1 to conjugate of alpha 1, right? To another root of the minimal polynomial of alpha 1 over K. And the number of such roots in general is the degree of that polynomial, which is exactly, so the number of such roots is bounded by the degree of the polynomial. You could have missing roots. You could have repeated roots, which will make you miss some opportunities to map alpha 1 to, the degree of the polynomial. And in any case, the degree of the polynomial is the degree of the extension, right? This is by definition, essentially. And so, right, so the number of ways you have to extend phi to K of alpha 1 is bounded from above by this. And there are two things that trouble you in getting equality here. One is that the polynomial may not be separable. And so, you have the automorphism have less choices. Maybe the degree is 4, but there are only two different roots. So there is only one option to take a root. And another problem that it could arise is that maybe this is a separate polynomial, but the roots are not in L. I mean, you have to map alpha 1 to a conjugate of alpha 1 that sits in L, at L. And so there are two reasons to lose here, but in any case, the bound is a bound. And then you can just repeat this argument. So now you can look at this triangle. No, maybe I should say this triangle, sorry. So you want to extend K of alpha 1 by any extension you had of phi from K of alpha 1 to L to an extension of K of alpha 1 comma alpha 2 to L. And here again, by the same reasoning, the number of ways to extend it, I mean, each of them is obtained by choosing where alpha 2 will go, and then everything is fixed. And alpha 2 can go to a conjugate of alpha 2 with respect to this field. So when you look at the minimal polynomial of alpha 2 over this field, it has this is the degree of that polynomial, and in the best case scenario where this polynomial is separable and L contains all the roots, you get equality, but generally speaking, you will have at most this number of roots to work with. And this continues on, and the proof follows because the product of these things is precisely at the end of the day M over K, right? Because this kind of cancels out. Good. Yeah, so here if you're going to look at the website or something, here you have what I said in writing, but let's just skip this one, this part. Okay, so the last thing I want to do is to prove this theorem 19, which is the main bulk of the lecture. And it gives 4 characterization or 3 other characterizations of a Galois extension, at least for finite extensions. And our extensions will be finite. So let's say M over K again is a finite extension with Galois group G. When the following are equivalent, so first of all, M over K is Galois, namely separable and normal. Secondly, the Galois group is exactly the same as the index. So if you remember the previous lemma, we know that the Galois group is always bounded by the index from above. So what this says is the Galois group is as large as possible. In a sense, it's the most symmetric that you can have. Well, good. So you see here there is no reference really to normality or separability. It's something about the way the group and the fields are related. The field extensions are related to each other. So in a sense, this is a more, I don't know, natural definition. It's an extreme extension in the sense that you get equality rather than inequality. A third way of saying the same thing is that K is exactly NG. So we said that when you look at a Galois, when you look at a finite extension, you look at the Galois group, it could be the case that the automorphism, in fact, actually picks larger elements that are outside of K. And a Galois extension is such that this doesn't happen. So any element that's not in K is moved by by at least one of the elements in the Galois group. And the fourth thing is that M is a splitting field of a separable polynomial, which is typically very easy to. This gives you a way of constructing examples, for example, because you can easily find a separable polynomial, look at the splitting field, and you got a Galois group, a Galois extension. Okay. Okay, so let's prove them one by one. We are going to prove, 1 implies 2, 2 implies 3, 3 implies 4, and then kind of easily 4 implies 1. So let's start with 1 implies 2. So let's remind ourselves what is 1 and 1 is 2. So I'm assuming that M over K is Galois, and I want to prove that the Galois group is as large as possible because recall the Galois group is bounded always by the index of the extension. Okay. So as a first step, or maybe I should. Right, so I know that the Galois, so just to remind us to have it here. So we know that the extension is normal and separable. And I want to show that this one. Okay. So first of all, let's fix our Galois closure K bar over K. That will be our L from the previous lemma. So we are going to embed everything in K bar. And if you consider the previous proof that we talked about, there are exactly K this number of extensions of phi due to the separability of alpha 1, and since k bar is algebraically closed. Right? I mean, going back to this thing, we said that the only reason you won't get equality here is that the polynomial is not separable. The minimal polynomial of alpha 1 is not separable, which will make you lose roots. Or maybe L doesn't contain roots that alpha 1 that are conjugate to alpha 1, right? In the same reducible polynomial. But since L in our situation now is k bar, it contains all roots, all conjugates, so all roots of the reducible polynomial of alpha 1. And because we assume separability, I'm not talking about normality just yet, then you have all possible roots. So you actually do have equality here and in all other steps as well. So really what I'm saying is that in this thing is that if you repeat this, there are exactly m choose k extensions of phi to k bar, right? Where L is k bar, because you haven't lost in any steps of the way, any of the steps in the way, on the way. But that's to k bar, not to m. Right? I want to show this thing is true. Not I want to talk about the Galois group of m over k, not of k bar. And so far I haven't actually even specified m. Besides, well, actually I did break, and that's not true. I did break the steps were broken according to m, but I didn't use the normality of m. And so here we only use the separability, and that m over k is finite. So, but the point is that because we identify k with its image, phi of k in k bar, namely, I'm essentially considering phi to be the identity on k, since m over k is normal, each of the embeddings that we just found, from k bar to k bar fixing k, actually maps m to m. Right? If you restrict it to m, it will map m not to some copy of m within k bar, but to m itself because of the normality, and because we are identity on k. And so really, each of the automorphisms, the large in k bar automorphism found, can be restricted to an automorphism of m, and therefore you did get this equality. Good. So now let's move on to implies 3. So 2 was, the assumption that the Galois group is as large as possible, and 3 was that k is MG. Namely, only those elements in k are fixed by all elements in sigma. Okay, so let's see. So again, let's denote by G. Sorry, if you remember, G was the Galois group of M over K, and what I'm claiming here is that G is actually the Galois group of M over Mg. So why is that? So let's move the two directions. So on one hand, we know that K is a subset of Mg, regardless of what Mg. I mean, we just know that, and regardless of what Mg is, just this thing implies that. Right, because K is a subset of this subfield of this field, then here you have all automorphisms that are required to be identity on K, and here you require more. You require those automorphisms to be identity on Mg, which is a larger field, kind of regardless of the nature of this field. So clearly, every automorphism here is here, because if you are fixed on Mg, you are fixed on your identity on Mg, your identity also on K, which is a subset of Mg. So that's kind of without using the definition of Mg, just because Mg is larger than K. But on the other hand, by the very definition of Mg, we know that for every sigma in the Galois group of M over K, we know that sigma acts as the identity on Mg, and that was Mg. That field, subfield of M extending K, such that for every sigma in G, sigma acts as the identity on that field. So that's the definition of Mg. And so for every sigma here sits here as well. So we have this reverse inclusion, and so we get equality. These two are the same. It's very simple, but it's a bit kind of logically confusing, I think. Anyhow, so we know that G is the Galois group of M over Mg. And therefore, by lemma 17, but we apply it to M over Mg, right? Lemma 17 was this one. Now, this one that says that the Galois group can be as large as the index of the extension, but now I'm using it not for M over K, but I apply it to M over Mg. So we know that the Galois group can be at most this thing, right? And this inequality is obvious just because Mg contains K. It's a larger field, so the index is smaller. But so far we haven't used the assumption, but the assumption kind of close the cycle, because the assumption is that the extension is of size G. This is the assumption. And so we get equalities all the way, which in particular means that Mg equals K. Right? Because everything here is, these are equalities in K is a subset of Mg, so the only way around it is for Mg to be K. So alternatively, you can write this thing as M. Sorry, you can write this thing. Oh, I got way too far ahead, sorry. Oh, I got to a different, yeah, I got to a different slide. Okay. So you can write this thing as M over Mg times Mg over K times Mg over K. And because you have equalities on the way, it means this is 1, and so Mg equals to K. Good. So the next one is, under the assumption that K equals Mg, you want to prove 4, which means that M is the splitting field of some separable polynomial. So let's see. M is the splitting field of a separable polynomial. Okay, so is this true? So take any alpha that you want in M. Generally, soon we are going to choose them in a particular way, but take any alpha in M, and for that alpha is define this polynomial, the standard polynomial that you define in these settings. So you look at X minus all the conjugates of alpha according to the Galois group of M over K. So you just look at X minus sigma of alpha iterating over all sigma in G. And, if you look at it for a second, then the coefficients of this polynomial are fixed by every element in G, right? Because if you take any, say, tau in G, I don't want to call it sigma because you have this running index here. So if you look at tau in G, and you apply it to, if you apply it to G of alpha, then tau respects multiplication, so it goes through the product, and so you get a product of tau of X minus, so it's just X minus tau sigma of alpha, where sigma iterates over all element in G, and that's just reshuffling. It's the same polynomial, right? It's so that's also G of X. Tau just take the product in a different order, maybe, but it's the same thing altogether. So so this means that the coefficients, so it's the same polynomial. So the coefficients, I mean, on the other end, you can write G in terms of its coefficient expansion, and it will tell you it's the same polynomial, so the coefficients stay put. And so this means that all coefficients are precisely in Mg, because Mg is this set of elements within M that are fixed by all taus in G. Now, per our assumption, Mg is K. Okay, so what we got is that actually this polynomial, per our assumption, is over K, because of the symmetry that we have that is in Mg and the assumption that Mg is K. Now I want to tweak this a little bit because G of alpha is not a separable polynomial. I mean, it could be that sigma 1 and sigma 2 in G could be the case that sigma 1 and sigma 2 in G satisfies sigma 1 of alpha equals sigma 2 of alpha and so forth. So what you should really do is to take just one representative out of each of those, and you can also show that indeed still the coefficients are in K and so forth. So you don't really look at G of alpha, you look at G of alpha where you only take one sigma of G for which you get the same answer, the same So if, for example, sigma 1 of alpha equals sigma 2 of alpha, you just take sigma 1, you don't take both of them. Okay. You need to slightly worry a little bit and, show that actually even that, even when you do that, the polynomial is the coefficients of the polynomial are in K. But anyhow, having done that, because m over k is finite, in particular finitely generated, you can write m as k of some alpha 1 up to alpha n, and the polynomial that you are looking for, the one that makes m over k a splitting field of that polynomial, is just going to be the product of the g alphas for those alphas, so the field of I. Well, again, just to make sure that you are separable, if alpha 1 and alpha 2 are conjugate, but you don't take both of them, you take just one of them. And that's, of course, always enough. So, yeah, so then kind of obviously m over k is going to be the splitting field of G. G is separable because we made sure it is separable in both steps. Now, the last step is 4 implies 1. So 4 means that f is the splitting field of a separable polynomial. And 1 is just the usual definition of Galois, which is normality. So the extension is normal and separable. And why is this true? Well, if you remember, when you talk about a normal extension, we said that splitting fields are always normal. So by the assumption about the fact that this is a splitting field of some polynomial even when it's normal. And because it's the splitting field of a one separable polynomial, then the extension is clearly also separable, because you only adjoint to k some finite number of separable elements, making it separable. Okay, I think that's kind of enough for the background you need from Galois. We'll stop here. Of course, in a normal Galois theory course, you also prove the correspondence between the subgroups of the Galois group and the subfields of the field extensions of. But I won't need that. Actually, mostly we need results about separability and normality and the characterization and working with embeddings and automorphisms, which is what we kind of practiced so far. But if you want, you can look at the slides here and so forth. But generally, again, I recommend looking at Richard's videos, kind of far better than what I will give you anyhow